In this video, we're going to take a look at solving radical equations. And we're going to just begin by looking at a really straightforward one. Square root of x is equal to 5. This symbol here is a radical, and this is a square root. When you just see this symbol, if you see things like this, right, the cube root of x, that's also a radical. And just a quick reminder here that, because this will be something you'll run into at various times, that if you have a root, the nth root, so this could be like a 3 in this case, or in this case where it's not written, a 2, and then you have x raised to a power, that's equal to x raised to the m over n. So a radical expression can be turned into a rational exponent expression. And then more simply, if you just have the nth root of x, that's equal to x to the 1 over n. So, for example, this is the same as x to the 1, because there's a 1 on the x over 3. And so that's the definition of what it means to have the cube root of x. That's the same as x to the power of 1/3. All right, so with all that, yes, this is x to the 1/2. And with that idea that it's x to the 1/2 and the desire to get x by itself, that kind of leads us to our algebraic technique for solving equations like this. Now, this one you might look at and just know, okay, the answer's got to be 25, right? Because the square root of 25 is 5. But the algebra that's doing that is we are squaring both sides of the equation, right? If this is x to the 1/2, squaring that makes the 2 times 1/2 turn into a 1. So x is equal to 25 is our solution. All right, and we can apply the same exact idea to something like this. So if I have the square root of 3x minus 2 equals 5, and I square both the left and the right side, then the square and square root essentially zap each other. And the only difference between this problem and the last one is I just have a few more algebra steps to take before I'm completely finished. All right. Okay, so in this one, we have a situation where we've got a square root of 6x minus 5, and then there's an x outside the square root as well. So let's first understand that the reason in this last one why the square and the square root just eliminated is because the square root is the only thing I was squaring. If I were to try to square multiple terms, including a square root and other terms, then you're going to have to multiply out in a more complicated way, like maybe foiling or something like that. So our first step should always be to get that square root by itself. So we don't even want to consider squaring both sides until that's isolated. Kind of like when we were solving absolute value equations. We don't want to kind of get rid of our absolute value until the absolute value is isolated. Same thing here with the square root. So now I can, of course, square both sides, but because there's an x on the other side, that leaves us with a quadratic equation. That's okay because I know how to handle this, right? If you have a quadratic equation, we should start by making one of the sides equal to 0 most of the time, especially if there's a middle term. And, we have lots of tools at our disposal, right? We've got the quadratic formula, we've got completing the square, we have factoring. This is one where factoring is quick and really easy to check to see if it'll work. So I would just probably try to factor it real fast because this would be quicker than the quadratic formula if it works. So I know that I would need a 1 and a 5 to make 5, and they would both have to be minuses so that it made negative 6x when I added the outside and inside, and that works. So we have x minus 1 equals 0, so x equals 1, and x minus 5 equals 0, so x equals 5. All right, great. So the one other thing that we probably should do, this is a new type of equation, so we should check our work, right? So let's go ahead and do a check. Let's check x equals 1. Let's make sure that this does in fact work. So if I plug in one for x, does that equal 0? Well, I have the square root of 1 minus 1. Yeah, that equals 0, so that checks out. Let's also check x equals 5. So if I have the square root of 6 times 5 minus 5 out here, does that equal 0? Well, 30 minus 5 is 25. So yes, that checks out as well. All right, so I'm comfortable now saying that both of these are solutions to that original equation. So to just kind of summarize our steps for solving a square root, we want to isolate the radical. We want to raise each side of the equation to the power that's equal to the index of the radical, and really to the power of 2 for square roots. I was giving instructions that are more general that work for cube roots and fourth roots and things like that. But I did specify square root up here, so that's really all we're going to look at. Then we solve for x, of course, and then it is important to check all your potential solutions. And just to kind of spoil it a little bit, I wasn't just checking in the last problem to make sure I didn't commit an error. There's a really important reason why here with radical equations we always need to check our solutions. All right, so let's go through this process here, right? Isolate the radical. So the square root of 9 plus x equals 3 plus x. And we need to square both sides. Now, just a little aside here, this is a good opportunity to just point out that while over here, the square and the square root just eliminate, and I have 9 plus x. Here, remember, you've got to write this out in FOIL, right? You can't just square each term. That's a path to definitely getting the wrong answer. So, right, this is really 3 plus x times itself, right? So make sure you write that out. Then you can go ahead and do the rest of that. So it would be 9 plus 3x is 6x plus x squared. And again, it's a quadratic, and I know how to handle that. So we'll subtract 9 and subtract x from both sides. So I have 0 is equal to 5x plus x squared. Now here's a quadratic that's missing the constant, and whenever that's the case, right, we should think about just easy factoring, right? X can come out of both terms. So this leaves me on the one hand to x equals 0, and then on the other hand to x is equal to negative 5. So check, right? We want to check. So if I check x is equal to 0, the square root of 9 plus 0 minus 0, does that equal 3? Sure it does, right? Okay, but what about the other one? Check x equals negative 5. So I've got the square root of 9 plus negative 5, okay, minus negative 5. Does that equal 3? So here the square root of 4 plus 5. Does that equal 3? Well, no, that's 2, right? So 7, of course, does not equal 3. So what's happening here is that one of our potential solutions is not working out. So this ends up being our only solution. This can happen when you're solving radicals where you end up squaring variables on both sides like we did right here. Now what's occurring is it's possible by the way that we did the algebra to turn a false statement into a true statement. And here's what I mean. Notice that if you plug -5 in here, right? So if you go x equals -5, at this stage you have the square root of 9 plus -5 equals 3 plus -5, which is going to just be 2, right? Square root of 4 is 2, equals -2, which is of course nonsense, right? But what did you do in the very next step? In the very next step, you squared both sides. But if you square the 2 and square the -2, what do you end up with? You end up with 4 equals 4. So what you've done by squaring both sides is you've actually turned a false statement into a true statement. And you didn't know it because you didn't know what x was back here. So we check for that. It's called an extraneous solution. This is an extraneous solution here. It's not a part of our solution set, and so we're essentially kicking it out because even though we thought it worked out, by checking we realize it's not a true solution. All right, just one more example here. All right, we know the drill. Get the square root by itself. Square both sides. All right, so we have x plus 1 is equal to, and we remember to FOIL this thing out, right? So you don't necessarily have to write it out every time, but maybe to the side, make sure you are doing this process. So 64 outside is -16x, inside -16x, so minus 32x plus 4x squared. And then I can subtract x, subtract 1. So we have 0 is 63 minus 33x plus 4x squared. And here, and I always like putting the oops, my eraser there. I always like putting the leading term first, in case I decide to go ahead and use factoring. I always just feel like that's in the most comfortable position for me if I have it in this descending order, square term, x term, constant term. All right, now I'm looking at this and I'm thinking, this very well may factor, right? Very well may factor, but the numbers are starting to get larger. So I would be okay here with, even if it does factor, if you would rather say, I'm just going to do the quadratic formula. That's fine by me, right? The quadratic formula is a tool. So to say x is the opposite of -33 plus or minus the square root of -33 squared minus 4 times a, which is 4, times c, which is 63, all over 2a, 2 times 4. Let's see how all this comes out, right? 33 plus or minus, and we've got a big mess in there, so if I take 33, or -33, I guess, squared, minus 4 times 63, I end up with 81 inside that square root, which is actually great news because square root of 81 is 9. And the fact that I'm getting a nice square root there means I could have factored, right? But there's no harm in using the quadratic formula either. So here we have x equals 33 plus 9, so that's going to be 42 over 8 when we use plus. When we use minus, x equals 24 over 8. And so if we go ahead and reduce there, 21 over 4, and reduce here, there's a 3. Okay, so with all that, we do still need to check our work. And forgive me for not leaving a ton of room here, but let's go ahead and check. So I'm going to wall this off here. We're checking. So we'll check, 3 is easier, right? So let's start with that. We'll check x equals 3. And so we have 2 times 3 plus the square root of 3 plus 1. Does that equal 8? Well, pretty quickly we can realize yes, because it's 6 plus the square root of 4. That definitely is equal to 8. All right, but what about the other one? So let's check x equals 21 over 4. Be a little bit more work here, I suppose. So we have 2 times 21 over 4 plus the square root of 21 over 4 plus 1. And that is supposed to be equal to 8, right? We don't know yet, though. So here we get a little bit of nice reducing, which we can show with here. So put a 2 there. And then inside here, we're going to want a common denominator. So we have 21 over 2 plus the square root of 21 over 4 plus 4 over 4. Does that equal 8? So 21 over 2 plus, so this would be the square root of 25 over 4. Does that equal 8? Well, 25 and 4 are both perfect squares, so this will be 21 over 2 plus 5 over 2. Does that equal 8? Well, 26 over 2 does not equal 8. So what we find here is that x is equal to 3 is our only solution. And of course, we can identify what's happening here because look, if you plug 21 over 4 in there, what you end up getting is 21 over 2, which is bigger than 8, so you get a negative on this side and a positive on this side. And just like in that last problem, you square both sides and it becomes a true statement all of a sudden. So x equals 3 is the only valid solution.